Okay, so welcome back to class. Quite a few things to chat about really quick today. Um, so plan for today is to just continue with chapter 7, confidence intervals. So we talked briefly about confidence interval for the mean of standard deviation is known and for the proportion last time. We'll review that material, go through another couple examples, and then talk about confidence interval for the mean when standard deviation is unknown, and possibly continue on from there depending on how far that takes us. Also, um, this next confidence interval topic, as well as another future one, are going to depend on different tables. So let me post those in the chat. Let me get those over here. Okay, so there are two other tables, kind of like the normal distribution table, how we have a set of these like areas under the curves versus indices related in a table. I posted two more PDFs in the chat just now, the chi-square table and the t-table that we'll be using throughout chapter 7. So take a look at those. You might want to download those, save them to your desktop, something like that. But if you lose track of them, they're also posted in Blackboard or on Blackboard in the supplemental materials folder in the chapter 7 and 8 subfolder. So go to supplemental materials, chapter 7 and 8. You should find them in there as well. And of course, they're in your textbook in addition to all of that. So, but this way you have them in an easy portable PDF form. Recall that Unit 2 exam is this week. I do recommend not waiting till the last minute to take it, planning to take it on or before tomorrow night. That way, if anything does happen, you have some buffer time before the due date of Sunday night. And then I forgot to write it here, but we do have spring break next week, so enjoy the break. However, I would recommend not stepping completely away from your schoolwork for the entire week or week and a half, depending on, if you have any Thursday or Friday classes. When we come back, we have a pretty quick turnaround before finals. So we have maybe a couple instructional weeks and then final exam week. And if you kind of step completely away from all of the material in all of your courses, or especially in a course like math where things tend to build on themselves, it can be tough to get that momentum back up in preparation for the final exam. So I do recommend, you know, uh, certainly take a break over spring break, enjoy it, but touch base with the material maybe 2 times over that week, really in all of your classes, I would say. Maybe something like Monday or Tuesday, devote, say, half a day to just reviewing some material, just keeping, keeping pace with the course, maybe reading ahead a little bit, and then maybe again on, say, like Friday, Saturday, something like that, take another glance back at the material. So you're not putting in a full week, nowhere close to that, but touching base a little bit so that you can finish strong. And then, of course, once the semester is over, then you can take a nice 100% break from everything as you like. And then two quotes of the day today, both I think related to kind of a similar idea. The first one is by American chess grandmaster Maurice Ashley. And he has this somewhat famous quote that there are 3 types of trades: forced, fantastic, and foolish. And if it's not forced or fantastic, it's foolish. So what is his kind of underlying point here for those of you who aren't as familiar with chess? Well, I think what he's kind of saying is when you make a trade, when I say like trade my knight for your bishop or something like that, that's a fundamental structural change to the game. You can't really undo that, right? If I move my knight from here to there, I can kind of undo that move later on. But if I trade my knight for your bishop, that trade is done for the rest of the game. No takebacks. So be really careful when you're making kind of fundamental structural changes. And I think that's also Warren Buffett's quote: "There are no called strikes on Wall Street." Uh, so, a baseball analogy, if you watch a pitch go by in baseball, if that was a good pitch, it's going to get called a strike. But if you don't swing at a pitch, if you don't, buy an investment that you think might be a good deal, you're not going to lose money by not buying that investment. So wait for the really good pitch, so to speak. You can wait for the one that's right down the center. You don't have to swing at every somewhat reasonable pitch. So again, when you're going to make a significant change, like say investing in this investment versus that one, um, maybe do that with care. And I think the same can be said, in a lot of life situations when you're making decisions. There are some. I've heard this analogy too. I'll probably get it a little bit wrong, but it goes something like there are three types of decisions in life, like uh, hats, haircuts, and tattoos. So like if you put on a hat and your friend says it looks goofy on you or something, well, just take it off, like that's easy to undo. There's haircuts. It's like, well, if you get a wonky haircut, I mean, you know, you might look goofy for a couple weeks, but it'll grow out pretty quickly. If you get a tattoo, like pretty close to permanent. I know they can undo tattoos and things these days, um, but it's, much, much more permanent. So, recognize which decisions in your life fall into which categories, which can be easily undone, and which are more fundamental structural changes, right? Um, and the more long term and the more fundamental it is, the more care that might be taken to make that decision very, very well. Those are decisions you make, like, in the morning when you're fully awake and not stressed and kind of calm and happy with the world. Okay, so coming back to chapter 7, confidence intervals, and a super quick recap. We talked about this last time, so I'm going to go through this really quickly. We have the idea of an estimator. So for instance, X bar is an estimator of mu. We have a sample statistic that's estimating a population parameter. And really, this is a point estimate. It's our best guess. But a point estimate without an error bound is a really marginal value. So what we would really like is some idea of how good is this estimate. So we would really like to say something like, for instance, my best guess from mu is X bar, but I'm 95% confident that, roughly speaking, say mu is in some interval, lowered upper bound. We developed a p% confidence interval for mu. So we want essentially the middle p% distribution of the distribution of X bar, which is our best guess for mu. I also noted that when I say X bar, when I say X bar as it is here, I'm talking about the random variable X bar. When I refer to X bar observed, I don't know why it is my allergy is always like, as soon as I start talking during class, my allergies flare up for like 10 minutes and then seem to get a little better. But whenever I say X bar observed, I'm talking about the specific value of the mean that we got from a specific data set. So I got into the world, I collect some data, that gives me a data set. I have an X bar observed that I observe from the world, but I understand that that's one instance of the distribution of the random variable X bar. And we developed this confidence interval. We called it X bar observed plus or minus a margin of error, where that margin of error is Z alpha over 2. Alpha here is the error rate. It's 1 minus the confidence level. So take half of that, putting half of the error rate in each tail, and get the Z index corresponding to that, and then multiply that by sigma X bar by sigma over root n, coming from our central limit theorem. We did mention a technical detail that really we ought to report this confidence interval as something like there's a 95% chance that an interval constructed using this process would cover the true population mean mu. It's really the interval, it's really L and U that are random. That's coming through the randomness of X bar observed. It's really not mu that is random. If I said something like there's a 95% chance that mu is in this interval, that would be incorrect. That's really a Bayesian statement. And as I mentioned before, you might say, okay, well, what's the likelihood that I fundamentally mislead someone, that I, cause them uh, to come to a conclusion that is not in line with the results by making this mistake? Probably not too great. But the thing is that a similar mistake in hypothesis testing in chapter 8 can actually cause quite a bit of confusion and quite a bit of difficulty. So we want to really, try to get this technical detail correct at this level. So we move into chapter 8. It's a little more natural. We also mentioned that we have a confidence interval for P, the population proportion or the probability of an event, given P hat the sample proportion. So P hat is the observed number of successes over the number of trials. Again, this is a good estimator for P. And under the assumption, the rule of thumb that we have at least 5 successes and 5 failures, P hat is approximately normal by the central limit theorem with a mean of P hat observed and a standard deviation of P hat observed times 1 minus P hat observed over N, all under the square root. And again, as I mentioned last time, I'm being a little bit fudgy here. Normally, we would say that this would be P, the population proportion P, but we're using P hat observed in place of that. And I mentioned that there's really a kind of behind the scenes technical detail that says that we could basically do this and the math ends up the same. So really we should be looking at the distribution of, say, something like P minus P hat observed, but then P is just a constant and we're shifting everything by a constant. So we can essentially treat it like this. Okay, so we can construct our capital P percent. Sorry that there are so many P's floating around. We use P for a lot of things here. You probably P standing for probability or proportion. So it comes up a lot in stats. We'll see in chapter 8, we have a P value, which is another use of the letter P. So anyway, we construct a P percent confidence interval for the population proportion little p in a similar manner. We have our point estimate, P hat observed, plus or minus a margin of error. And the margin of error is a z-score times the standard error. This standard error is the same thing that came out of the central limit theorem for proportion. Okay, so that was a really quick review crash course of what we covered last time. So certainly not the pace of a first introduction, but hopefully that kind of reminded you of all of those little details. And we're now ready to go into these two examples that we didn't finish up last time. Okay, so example 2 here. A company wants to know the average price of novels on the market. Assume that prevailing market knowledge suggests that sigma equals $3. The population standard deviation is $3. The company takes a sample of size 25, and the sample mean price is X bar observed equals $14.5. And we will assume normality here. Since we have a normal underlying population, even with a sample size below 30, we can still apply the results of the central limit theorem with no problem, and we can construct our confidence interval. And our goal is to construct the 90% confidence interval for mu, the mean price of a novel. Let me get my normal table up here and switch my screen. So just give me 1 second to do that. Let me get my windows scaled properly. Okay. All right, switch my screen share here. All right, so we know that our lower and upper bounds look like X bar observed plus or minus our margin of error. So let's find our margin of error first. It's going to be a z number. We'll come back to that in a minute, times the standard deviation of the underlying population, sigma x, or just sigma. That's $3 divided by root n divided by root 25. Now I know that my confidence level is 90%. So 90% of the time I'll successfully construct an interval that covers the true mean mu. But that means 10% of the time I make a mistake. 10% of the time I construct an interval that maybe falls completely below mu or completely above mu. and I missed the mark. And I want to split that error between the two tails. So alpha over 2 is 5% error per tail. Right, so I have a right tail area of 5% and a left tail area of 5%, and then like kind of a middle area of 90%. So Z alpha over 2 is the Z index. Z alpha over 2, or Z 0.05, is the Z index with 5% area to the right of it. And as we said before, it's usually easier to use symmetry here, find 5% area to the left. That'll give me a negative Z index, then just switch it to a positive. So using symmetry is usually the way to go here, I think. Although if you wanted to think of this as the 95th percentile of Z, you could do that as well and use complementary events. That would work perfectly fine also. So I'm looking for about 0.0500 on this table, and I see it falls between 0.0505 and 0.0495. Like usual, I know this is really small on your screen, so I'm kind of expecting you to work along with your own either PDF or physical copy or something of this table. But I'm looking for an area to the left. Remember, we're using symmetry, so area to the left of 5%, and that falls right between these two. And I see the note down here, it says use negative 1.645 as your Z index. So there's 5% area to the left of negative 1.645. Well, then there's 5% area to the right of positive 1.645. So that's our margin of error calculation. Let's figure out what that is. Bring up the calculator. So it is 1.645 times 3 over, and square root of 25 is just 5. So that's 0.987. And just a reminder, keep in mind this is in units of dollars, because this 3 is in units of dollars. The z-score and the root n are just unitless numbers. So this is just under $1, or about 99 cents is our margin of error. And then I can say my 90% confidence interval for mu is, well, I need a lower bound and an upper bound. My lower bound is what's X bar observed. That was $14.50 minus, let's call it just 0.99, or that's what, 13.50 plus 1 cent, 13.51. And my upper bound would be 14.50 plus 0.99, or that's 15.49. So 13.51 up to 15.49. So I'm 90% confident that this interval, $13.51 to $15.49, will cover the true mean mu, the true mean price of novels of this type on the market. Okay, let's move on to any questions on that one first. I think one of the really kind of nice and interesting things about chapter 7 and 8 is really all of this math looks familiar, right? We've seen z-scores before. This is just basically rearranging a z-score, right? Z equals x minus mu over sigma, or x equals mean plus z sigma. That's really what we have here, mean plus z times a standard error, a standard deviation of the normal distribution coming from the central limit theorem. So we've seen all of this math before, but we're just combining it in an interesting way to do something that that I think is greater than the sum of its parts, something like that. We're combining some chapter 3 ideas that just looked inside of the data we're combining that with some chapters 4 through 6 ideas that looked at purely abstract mathematical models, and we're coming up with something that is making an inference about real world information on the basis of these previous bits of material. So we haven't really introduced any new math here. We've introduced new logic and new ideas, combining things together in an interesting way. Okay, so example 4. So again, last time we did example 3, the kind of die roll example with 21 ones on 100 rolls, and what was the confidence interval for the probability of rolling a 1. Here we have a very different scenario, but it's a similar type of problem. We're interested in knowing little p, which is the probability that a voter votes for candidate A. Exit polling conducted between 3 p.m. and 4 p.m. on election day reveals that 539 out of 979 people polled voted for candidate A. We have a multi-part question here, but let's start with the first part. Let's construct a 99% confidence interval for P, the true probability of voter votes for candidate A. So what do I know? And what do I not know? Well, of course, I don't know P. If I knew what P was, little p, the probability of voter votes for candidate A, then I would just tell you what it is and be done with it. We wouldn't be estimating it. What do I know? Well, I know number of votes empirically is 539. Number of trials, 979. So there were 979 people I asked, and 539 of them were successes in the sense that they responded in the way that I'm looking for, that they voted for candidate A. So I know p hat is, and let me be a little more specific, p hat observed is 539 out of 979. So I know p hat observed. I know n, of course, this is n. And I know my confidence level. My confidence level is 99%, which tells me alpha is 1%, and alpha over 2 is 0.005. Be careful, 0.05 would be 5%, but we want a 0.5%. We want 0.005. So be careful with the number of decimal places there. So let me start by finding my margin of error. My margin of error is going to be a z number. I'll find that in a minute here. Times the square root of p hat observed times 1 minus p hat observed over n. Well, I know the over n over 979. What is p hat observed? Let me calculate that. Come over here to my calculator and do 539 over 979, and that's about 0.55. So the polling indicated about 55% of people sampled voted for candidate A. And then, of course, 1 minus p hat observed is 0.45. Extend my square root out there a little bit. Okay, so I've got that bit, and now I need the z index. So I need z alpha over 2. So 99% confidence means 99% in the middle, and then 1% combined between the two tails, or that's 0.5% in each tail. So I need area to the right of z alpha over 2 is 0.005, or I find an area to the left of 0.005, and then use symmetry to take that negative index and make it positive. I actually see that 0.0050 is right between 0.0049 and 0.0051. That's another one of these special cases. And it's indicated because these come up often, and we can get a little more accuracy here. So for 0.5% area to the left, that Z index would be negative 2.575. So 0.5% area to the right, we just flip it over that zero axis to positive 2.575. Okay, we've got to plug this in the calculator now. Let's see what we get. So I have 2.575 times everything after this goes under the square root. So I do second square root. And I need 0.55 times 0.45 divided by 979. And let's end that parentheses. Check everything. Does that look good? Looks good. And this gives me 0.0409. Or let's call that about 4.1 percentage points. One little note on this margin of error, all of these numbers are unitless. Number of successes, number of trials, so therefore p hat observed, the square root, everything here is unitless. So this error is just a number with no unit. It's essentially like a number of percentage points. To finish out our confidence interval, we say our 99% confidence interval for P, the probability the person votes for candidate A. Well, we have a lower bound and an upper bound. The lower bound is P hat observed. Well, that's 55% minus the margin of error, minus 4.1%. And the upper bound is 55% plus 4.1%. So for my upper bound, this would give me 59.1%. And for my lower bound, so that would be what? 51% minus 0.1%. So 50.9% for the lower bound. So I can say that I'm 99% certain that this interval, 50.9% to 59.1%, will cover the true population proportion, P, the true probability that a voter votes for candidate A. Okay, question B, simply considering the statistics, simply looking at the numbers, on the basis of this exit poll, should we be able to call the election for candidate A? And the answer is essentially yes, right? The lower bound here is 50.9%, and assuming that this election works the way that most of our elections in the US work, that if you get the majority of the votes, you win. So if any candidate gets more votes than all the other candidates, they win. But it's certainly true that if any specific candidate gets more than 50% of the vote, they necessarily have to have gotten more votes than any other candidate, right? So a candidate could win with, 48% of the votes or something like that if there were more than two candidates running. But certainly if a candidate gets above 50% of all the votes, they have to win. And we see that our lower bound here, 50.9%, is above 50%. So yeah, we probably can statistically call this for candidate A. Right. Now, there are going to be some times that we make a mistake that our interval just happened to be a little bit too high by chance. And maybe candidate A's true proportion is a little bit below 50%. But we should be successful 99% of the time. So statistically, can we call the election for candidate A? Yeah, yes, we can. Something that's actually really interesting here did the numbers, just the statistics that we calculated, care about the size of the population relative to our sample size of 979? Actually, no, right? Does the size of the population, the underlying population, come into play anywhere in here? No, it doesn't. For that matter, does the size of the population come into play anywhere up here? Anywhere in this formula? No, it doesn't. If we sampled 979 people in a US general election for, say, the president, or if we sample 979 people in some mayoral election for a small suburb of maybe 10,000 people, we would end up with exactly the same confidence interval. The statements being made here are statements about sampling error on the basis of the size of a sample, but we're not, that doesn't, that doesn't, the size of the population does not impact these statements at all. That being said, kind of like looking outside of the numbers at, say, common sense, things like that, should we call the election on the basis of the sample? Well, probably not. If this is a presidential election, 979 people are not going to be representative of our entire population across the whole US, right? Regardless of what the numbers say, I know that a sample of size under 1,000 is not going to be representative of, 100 or 150 million people. There's just too many ways to slice and dice all of the different aspects of the population for that many people that we could get a really representative sample of size under 1,000. We also note that this was an exit poll. So is there going to be some kind of bias introduced by folks who are willing to participate versus not willing to participate in exit polling? This random person standing outside of the voting area saying, who did you vote for? Well, some people will be willing to engage with that person, and some people are going to walk right past them, right? So there's a bit of bias there that's likely introduced. They did this in a fairly narrow time range. So, between 3 and 4 p.m., maybe you're getting, say, more retirees and fewer folks who are working. They might be working during that time period. It might have gone before work, or it might be going after work. Or maybe if you did the poll early, you're missing the say college students. A lot of college students aren't going to get up at 6 or 7 a.m. to go vote. They're going to maybe vote later in the afternoon. So maybe between 3 and 4, you're more likely to get people like college students. So should we call the election on the basis of the sample? Well, there's a lot of other considerations to take into account, right? And as kind of a side note, when we get into inferential statistics like this is where things get kind of messy, right? In math, if you look at, say, an algebra problem or a calculus problem, like we have the problem statement, we go through a very rigorous set of operations, we get the answer, and it's essentially inarguable what that answer should be. If somebody gets a different answer than me, we just go through our two different lines of logic and we figure out, oh, you made an error here, I made a logical misstep there. And we always get the same answer. There's very little debate over. But something like this, do I think that a sample of this size could be a representative sample? Maybe in a small town of 10,000 people, it's a very good sample, very representative, right? But in, say, a US general election, probably too small to be representative. But that's a judgment call, right? So two different people who are very well versed in statistics and very well versed in statistics applied to voting can look at exactly the same numbers and come to somewhat different conclusions. I think it's kind of hard to come to polar opposite conclusions on the basis of the same numbers, but they can at least come to different conclusions where one person might say, oh yeah, candidate A won, no ifs, ands, or buts. Another person might say, I mean, I'm leaning toward candidate A, but not really sure. And another person could say, this is so far away from being representative of the population that it's essentially meaningless. We need a lot more data over a much broader time period, over a much broader, maybe geographical area, and a much larger N before I'd be confident really saying anything. I don't think too many people could look at this and say this is clear evidence against candidate A winning, but you could have a pretty substantial range of interpretations here that I think would be reasonable from reasonable people. Um, right. So statistics is kind of it's like math. We did a lot of calculation, but when we're actually interpreting numbers and saying what should we do on the basis of this, what knowledge does this actually represent about the process we're studying, the likelihood of a general voter to vote for candidate A, there's a lot more gray area than it might at first seem. Okay, and then back to a mathematical question. So we did this calculation here based on this sample, and we got a margin of error of 4.1 percentage points. Maybe we're unhappy with that margin of error. Maybe we say, well, I would like a smaller margin of error than that. To get a smaller margin of error, well, for the same confidence level, so Z is fixed because it's determined by the confidence level. Roughly speaking, the p-hat observeds are fixed. That's kind of just what we get from the sample. We can't change the p-hat observes at our will. So if we wanted to reduce the margin of error, if we wanted a smaller margin of error, the one lever, so to speak, that I have is n, the sample size. So if I want the margin of error to go down so that my confidence interval is tighter and I have something like a more precise guess at where the population proportion might lie, that corresponds to n going up. I need to, and this kind of just morally makes sense. I need to do more work. I need to take a bigger sample. What if I want a margin of error of at most 1 percentage point, assuming that p-hat observed remains the same? I noticed that n is under the square root, so going from 4 percentage points down to 1 percentage point means I want to cut the margin of error by a factor of 4. So I need a factor. Oh, how did that happen? I need a factor of 4 or of 1/4 coming out of here, which means this n needs to be multiplied by 16. I expect an answer somewhere in the ballpark of 16,000 for my sample size. Let's see if that comes out in the wash. So I want my margin of error to be 1%. But what is it actually? It's actually going to be, my confidence level didn't change, so my Z alpha over 2 stays the same, 2.575. By assumption, we're assuming that our p-hat observed remains the same. If we wanted to be extra conservative here, we would switch our p-hat observed to 50-50. So 50% here and 50% there. That would maximize the margin of error. And any other p-hat observed that we would get that is away from 50% would only reduce it further. But we have already a reasonable guess at what we think p-hat observed is, so we'll use that guess. So 0.55 times 0.45, and then over n, and we want to figure out what n needs to be to make our actual margin of error at most our desired margin of error of 1 percentage point. I see I can divide by 2.575 and square both sides. And now I can multiply by n and multiply by the inverse of 0.01 over 2.575 squared. We get a little more room here. So multiplying by n puts an n over here. I still have 0.55 times 0.45 on the right. And then I multiply by the inverse of this to give me 2.575 over 0.01 squared. Let's figure out what that right-hand side is. So I have 0.55 times 0.45 times parentheses 2.575 over 0.01, and that needs to be squared. Does that look right? That looks right. 16,410 or so, or n has to be at least 16,411, and that was about what we guessed. We had to reduce the margin of error by a factor of 4, since the n in the denominator is under the radical. After I square root the n, I need to have a 4, so that means the n has to be like 16 times as big. And we started out with an n of around 1,000, so around 16,000. That's exactly what we expected. So to get down to a margin of error of 1 percentage point, we would need a sample size 16,000 or so. We'd have to do a heck of a lot more work. Okay. Any questions on any of this? Okay, let me pause my share really quick here so I can swap out my tables. I'm going to bring up the T table now. Okay. Okay, so this next topic, confidence interval for mu when sigma is unknown, is going to use this other table called the T table. It's the one that I labeled Triola T table, and it's the one that looks like this, the T distribution. So let's take a look at the general idea here. Remember that our previous confidence interval for mu was when sigma was known, when a population standard deviation is known. That's when we got a z-score and so on. Now, I kind of mentioned before that it kind of feels unlikely that we'd be in a situation where we would not know the population mean, but we would know the population standard deviation. Probably much more likely that if we don't know the population mean, we also don't know the population standard deviation. And that's really what we're looking at here. So this is a bit more realistic of a scenario, but we'll also see it's a little bit more complex. We have to use a different distribution, the T distribution. Now, that being said, it actually follows a lot of the same general patterns that we saw previously. So it's not going to look completely different. In fact, it'll look quite similar. But I think it was good to start with the Z distribution because we're more familiar with that one. Okay, so our goal is to construct a confidence interval for mu when sigma is unknown, when we're estimating sigma by S, the sample standard deviation. So here we'll consider something like a t-score or a t-critical number, x bar minus mu x bar over S over root n. Recall that Z was x bar observed minus mu per x bar over sigma over root n over sigma x bar. Not x bar observed there. This should be x bar, the random variable. There we go. So this was how the random variable Z related to the random variable x bar. And we see a very similar relationship here, right? Between the random variable t and the random variable x bar. So what do we know? We know our sample stuff. We know our sample size. We know our sample mean, x bar observed, and we know our sample standard deviation, s. We also know our confidence level, and therefore we know alpha. We know our error rate, so we know things like alpha over 2 and so on. And our unknowns in this case are 2. Both mu and sigma are unknown. So we're estimating two things. We're estimating mu by x bar observed, and we're also estimating sigma by s. Either one of these things could be far off of the true value. There's more uncertainty here. Previously, we were only estimating mu by x bar observed, and then we knew sigma exactly. Now we're also estimating sigma. There's clearly more uncertainty. There are more ways to make an error. There are more ways to make a mistake. So for us to maintain the same level of confidence, we need to take a wider chunk out of the real line. Our confidence interval has to be wider to compensate for this additional kind of underlying additional uncertainty. So again, when sigma is known, the central limit theorem says that this thing, x bar minus mu x bar over sigma over root n, is standard normal. But what about this quantity, x bar minus mu x bar over s over root n? Well, it turns out that this is distributed according to a distribution called the student's t distribution. That's the name of the distribution, just like the z distribution was the standard normal distribution. And usually this is just called the t distribution. So you see, like over here, it's just called t distribution, critical t values. The PDF for t, for the t distribution, looks like this. It looks more or less like 1 over 1 plus x squared. And actually, it kind of visually looks pretty similar to a normal distribution. If you plot 1 over 1 plus x squared on your calculator, or if you plot e to the minus x squared over 2, right, they're going to look pretty similar to one another. They both have this bell curve look to them. They both are peaked in the middle, symmetric about 0. This is 0, this is 0. Here's z and t. Symmetric about 0, peaked in the middle, tailing off to the sides. They look the same. The main difference, though, is as x gets large here, my tails go to 0 actually even faster than exponentially fast. Going to 0 exponentially fast is pretty fast already, but going to 0 super exponentially fast, e to the minus x squared, is extremely fast. Z like screams to 0 as you get away from the middle. And we saw that even a 3 sigma event happens like what, 1 in 300 times. A 4 sigma event, I think, is in the ballpark of 1 in 30,000 times. So it's very, very unlikely under a normal distribution to be more than a few standard deviations away from the mean. But t, though, it goes to 0 like polynomially fast. It goes to 0 kind of like 1 over x squared, more or less. So its tails go to 0 inherently more slowly. Not just more slowly like a normal distribution with a bigger standard deviation, but like inherently more slowly. So for a t distribution, it's more likely to be more standard deviations away from the mean. And kind of inherently so. Not just because maybe we make sigma a little bit bigger or something, but the tails go to 0 fundamentally more slowly than the normal distributions. It's also important to recognize that where z was the standard normal distribution and there was one and only one of them, t is a little bit like a standard t distribution kind of, right? This like z bit up here kind of looks like that t bit down there. But these, we might call them the standard t distributions. There's actually a bunch of them. So where there's only one standard normal distribution, there's kind of a bunch of standard t distributions. So we actually have, say here, 0, and these are a bunch of different t distributions that are parameterized by a parameter called nu. the Greek letter n. So this might be, say, a t-distribution with nu equals, I don't know, 3 or something like that. Or let me make this a little bit, maybe make this like 10. And then maybe I have one like this. It's a little flatter and a little wider. Maybe this is like nu equals 3. This thing that looks a little bit like a V is nu. It's the Greek letter N. That's kind of like a curly V. Or something like this. Maybe this is like nu equals 30. One really interesting thing about the t distribution is as nu goes to infinity, the t distribution parameterized by nu goes to z. This is a really practically useful fact to know, and we'll see why maybe in a couple minutes here. But t distributions with larger and larger value of the parameter, what is called the degrees of freedom, they start to look more and more like normal distributions. This kind of makes sense, right? What's the main difference between z and t up here? It comes from us estimating sigma by s. But the larger the sample we have, the better an estimate of sigma we have in s, and the less kind of additional uncertainty is being brought into the fold by that estimate of sigma by s. So it kind of makes sense that as n gets large, t should look more and more like z, because knowing something about s is more and more like just knowing sigma precisely. So that's a nice property to remember, is that as the parameter for t gets larger and larger, that means sample size gets larger and larger. T starts to look more and more like z. Let me bump this down the line. And often nu, our parameter is n minus 1. Often it's 1 smaller than the sample size. There are a couple of cases where where our value for the parameter is different than that, but a lot of times it's somehow fundamentally related to 1 less than the sample size. Sometimes the calculation looks a little different in maybe some future chapters, but we'll see that it always really has this inherent relationship to 1 smaller than the sample size. Perhaps I shouldn't say always, but in the cases we'll look at, it does. Okay, so how might I want to construct a confidence interval then? Well, I want to lower an upper bound. I see t is symmetric just like z, so I should center my confidence interval at x bar observed. That makes sense. That should be x bar observed plus or minus a margin of error. So I want to take the middle, whatever percent of my distribution. That makes sense because t is symmetric and x bar observed is a good estimator, so it's unbiased. It's on average right in the middle. And then I do x bar observed plus or minus a margin of error. What should my margin of error be? My margin of error will look very similar to my previous margin of error. My previous margin of error for z was z alpha over 2 times, well, sigma x bar, my estimate for, or my standard deviation under the central limit theorem. So sigma x over root n. So here, the standard deviation I'm using is sx bar, which is just my sample standard deviation over root n. And in place of a z index, I'm using a t index. So I still have x bar observed plus or minus a margin of error. My margin of error is still index times central limit theorem standard deviation. But this gets a nomenclature change. It's s x bar instead of sigma x bar, or it's s over root n instead of sigma over root n. And my index, instead of using z as the distribution, I use t as the distribution. So theoretically, the two confidence intervals are quite similar, really just with this little, a little notational change using S here instead of sigma, and this change of using a different distribution. Now we do have a practical challenge we run into. So I set up here, there's lots of t distributions. One for nu equals 1 and nu equals 2, nu equals 3. This parameter nu comes into play. I could give you a t table like this normal table for the t distribution when nu is 1, and then give you another one for t distribution when nu is 2 and 3 and 4 and so on for a bunch of different nus. But that would be like a 100-page book that you'd have to carry around, or a 100-page PDF that you'd have to scroll through. That's not very efficient. But one thing that I kind of recall is that, well, when we were actually solving problems, the vast majority of the time we're looking for confidence intervals that are either 90%, 95, or 99%. Those are really the only three confidence levels that are practically used. Is it theoretically possible to compute a 93% confidence interval? Yeah, I suppose so, but nobody does it. So I really only need a few different z numbers, right? When we were looking up z numbers for these confidence intervals, we kept coming back to like this one, or the 0.0250, wherever that one was. Why am I having trouble finding it? I think I'm having trouble finding it because it's behind my cursor or behind my pop-up thing there. There it is, 0.0250. There were really only a few z indices when we were doing confidence intervals that we were interested in looking up. We kind of kept coming back to these same ones. These should be familiar now: 1.96, 2.58 or 2.575, and 1.645 or 1.65 or so. Those three numbers kind of came up several times. And it's because those are the three that are related to 90, 95, and 99% confidence levels. And in fact, if you look down here, there's actually a little cheat sheet. We were doing it the long way around just to get a little more practice with the normal table. But there's even a cheat sheet down here on the normal table itself that says for confidence levels, here are your critical values. Here are your z indices. So if I realize this, I realized that while it was super important to have this whole table when I was doing normal distribution problems from chapter 6, I needed this whole table. If I'm just doing confidence interval problems, most of this table, the vast majority of this table, is wasted space. I could present to you all the information you really need for confidence intervals in this tiny table down here. So now if I can present to you the information you need about z in essentially a single line with just these three numbers, I can reimagine how a table might look. Again, I needed a fully fleshed out z table mainly for the chapter 6 material, but now that we're in confidence intervals, we don't need a fully fleshed out z table. We only need to pluck a couple of numbers off of that z table that are the important numbers for the confidence intervals or the confidence levels that we tend to use. So the practical change here is that because I don't want to carry around a book of 100 t distributions, one for nu equals 1 and one for nu equals 2, and you can see all these different t distributions that are kind of represented in this table. I don't want to carry around a full page for each one of those. What I can essentially do is list out their critical numbers. This list here is for the t distribution with nu equals 1, this 1 to the left here. It is essentially giving you these numbers, just listing them out. The trade-off is we have a little bit less information. If you, for some reason, wanted to do a 93% confidence interval, you could do it with this normal table. You could find, uh, 3.5 percentage points somewhere down here, like, and you could figure out what Z index goes along with that, and that's your, 1.81 is your Z index for, say, a 93% confidence interval, some silly confidence interval. You can't really get that off of this table. That's the trade-off. But we can get one table that handles essentially all of the t distributions that we would need to be able to handle. So what is the t distribution representing for us? It's representing essentially t indices, or what they're calling critical values, or it's the t index with alpha proportion area to the right. If I wanted an area to the left, I use symmetry and I take my index and just make it negative. Okay, so let's take a look at an example. I think a good way to just start working through this is to look at an example. So let's start by assuming that body temperatures are normally distributed, so central limit theorem applies. We take a sample of size 10, and that yields a sample mean of 98.25. So we have, under what do we know? X bar observed is 98.25 degrees Fahrenheit. A sample standard deviation of 0.3, so S is 0.73. And we know that our sample size, N, is 10. We want to construct a 95% confidence interval for the true mean body temperature. This, of course, tells us that alpha is 5% and alpha over 2 is 0.025. So this is kind of the total error, the total area combined between the two tails. And this is the one tail area. What do we not know? What we don't know, we don't know mu. We also don't know sigma. Okay, well, I guess the first thing we should, well, let me copy this down for quick reference. So I guess the first thing we should do is compute our margin of error. So the error is going to be a t index instead of a z index times s over root n. Well, s over root n, that's basically the same mechanically as we had done before, where it's just s instead of sigma. 0.73 over root 10. We need to find our t index, and this is the real practically difficult piece of this, right? This is the in the transition from the z interval to t interval. This is the piece that maybe is the most complex, and it's not even that bad. So for my t index, what do I need? Well, on one hand, I need to know what the area is in, say, my right tail. And on the other hand, I need to know what distribution I'm working with, which t I'm working with. So my degrees of freedom, or nu, is n minus 1. My degrees of freedom is 10 minus 1, or 9. 1 less than the sample size. As an aside, it's called degrees of freedom because, well, what we know, what we've observed from the real world is X bar observed. And that's as a result of 10 different data points. How many of those data points can I choose, or can I say allow somebody else to choose any way they want, and still be able to concoct a scenario where we come up with X bar observed? somebody could choose 9 of those data points any way they want, and we could use the 10th one to essentially balance the whole system at a balance point that we want. So if you leave me one data point whose value I can choose however I want, if you leave me one constrained variable, then you're free to choose the other n-1 any way you want, and we can always bring the average back to x bar observed. So that's why it's called degrees of freedom. You can choose 9 data values any way you want, as long as you leave a 10th value to correct and bring things back to x bar observed. Okay, so we have degrees of freedom 9. That tells us which t distribution we're working with. We're working with the t distribution represented in this line here. The other thing I need is, what's my one-tail area? My one-tail area, well, 95% confidence, that's the between the two tails is 95%. The combination of the two tails then is 5%, and in each tail, in a single tail is 0.025. So be careful at the top of the table here, there's area in one tail and area in two tails. It's actually a pretty good idea to check both. My total error, my two-tail area should be 5%, and my one-tail area should be 2.5%, and I see that corresponds to this middle column here. So I'm looking down this middle column with a one-tail area of 0.025, two-tail area of 0.05. I'm looking across the row corresponding to 9 degrees of freedom. That indicates the t distribution that I'm on. And I see their intersection is right here at 2.262. And that feels like a Z number, right? I mean, it's not like a number like 10 or a number like 0.3 or something. I want to be 95% confident. I know that's like roughly 2 standard deviations, but it's not exactly the Z number, right? What would the Z number have been if we actually used the Z number for a 95% confidence interval? We would have used Z of 1.96. So not Z of 1.96. My margin of error is a little bit bigger. I went from 1.96 to 2.262. My margin of error increased by, let's call it roughly 10%, 10, 15%, something like that. It's a little bigger. It's a little bigger because I'm also estimating sigma by S. This is taking into account the additional uncertainty from that additional estimate. Okay, so it's not the z-score of 1.96, a little bit bigger, but of course it's in the same ballpark. We wouldn't expect this to go to like 10 or 20 or something like that. For these degrees of freedom 1, those numbers are a little crazy because it's, for degrees of freedom 1, you only have a sample of size 2. So like really how good is your estimate of sigma if you only have a sample of size 2? But for kind of reasonable sample sizes, you see that, we're getting t indices that are in the ballpark of 2, 2.5, something like that. It's in the ballpark of the z index that's about 2, but just a little bit bigger, taking into account that extra uncertainty. Okay, so what is the value of this margin of error? What is the margin of error for this problem? Let's look at that on the calculator. 2.262 times 0.73 over root 10. So that's about 0.522. My margin of error is about 0.52. My sample standard deviation was in degrees Fahrenheit, so my margin of error is about 1/2 of a degree Fahrenheit. And therefore my 95% confidence interval for mu where sigma is unknown would be what? it would be my point estimate, X bar observed, or in this case, 98.25, minus my margin of error, minus 0.52, so 97.73 on my lower end. And then for my upper bound, I just do second enter, change the minus to a plus, 98.77. Again, the second enter trick isn't all that beneficial here, but if you had typed all this out in one line with a margin of error calculation in the same line, it'd be a little more helpful. So we have an inference now. We're saying we're 95% confident that the interval, 97.73 to 98.77, it's a very wonky 8, 98.77, covers the true mean mu. And this takes into account the extra uncertainty from estimating sigma by s. Do we think it's reasonable or feasible that the true mean could be 98.6? Well, 98.6 is in this interval. So yeah, it does seem kind of feasible or reasonable that the true mean could be 98.6. If the mean I was asking about, right, 98.6 is the like often quoted human normal body temperature, although each individual's normal body temperature varies a bit. But if I was asking about a temperature like, 99.6, I would say, I think it's unlikely or it's not reasonable that 99.6 would be the true mean because it's outside of this confidence interval. At this point, we're really touching on some ideas in chapter 8 hypothesis testing, making a binary decision. Do I think this is true, yes or no, on the basis of this kind of continuous information. But so we're even pushing it a little further than strictly confidence intervals here, but we see how natural it is to proceed to other inferential questions and answers on the basis of what we have here. All right, any questions so far? Okay, let's look at one-sided confidence intervals now. We're only going to do one example in one-sided confidence intervals. We'll do it in the T world, but this would apply just as well for a Z interval from U or even for an interval for a proportion. The idea is essentially the same no matter what interval you're dealing with. So suppose a sample of insurance claims yields the following information. Sample of size 31, so central limit theorem applies, and bigger than 30. X bar observed of $1,000. So for these 31 claimants, there was an average claim size of $1,000 and sample standard deviation of $3,000. So again, sample standard deviation, we're thinking T distribution here. We want to find the 95% one-sided confidence interval, an upper bound, negative infinity up to U, for mu, the true mean population claim amount. We want an upper bound for the mean claim amount. I always say that the words upper bound or lower bound with a little bit of caution. We're not saying this is an upper bound, like period, end of story. It cannot be above this. We're saying something like this is an upper bound with 95% certainty. So when I say a bound, I mean with 95% certainty. That's the context here. It's not a hard upper bound as like one might talk about in, say, an algebra class or something like that, that, this function cannot under any circumstances go above this number. We're saying this in the sense of 95% certainty. So at first, this problem looks quite difficult until we actually kind of think through it. Well, where did all of these previous formulas come from? It came from applying the central limit theorem, and we have something like a Z or a T distribution, in this case, T. But if we were doing this in Z, the picture would look exactly the same. And before I had an upper bound and a lower bound with 95% area between, and that split the error rate 5% evenly between two tails. What changes here? Well, all that changes is I just have an upper bound and no lower bound. I just have an area to the left of 95%. Really, the only thing materially that changes is I put my entire alpha in one tail, not alpha over two, because a one-sided confidence interval only has one tail where I can make an error. I can only make an error if I set the upper bound too low and it happens to be below mu. If I set the upper bound really, really high and it like really, really covers mu, I still have a success. I can't miss by setting my interval kind of too far to the right. I can only miss by setting it too far to the left. So I don't need to split my error rate between two separate tails. All the error rate just gets pushed into one tail. What does that mean for my formulas up here? Let me copy this down. Well, all that it means is that instead of t subscript alpha over 2, it's just t alpha. Alpha is just the area in the single tail, the error rate. Degrees of freedom is still n minus 1. And here I would say L or U, depending on whether I'm talking about a lower bound or an upper bound. And then I would use the appropriate either plus or minus, but not both. So here I would use U equals X bar observed plus, right, we're going X bar observed plus a margin of error to the right for an upper bound and to the left for a lower bound. So for a lower bound, I use minus. T alpha, so I only go plus, and then I have T alpha. I put all of the error into a single tail times S over root N. So if you think through the picture, it's a perfectly easy change to make. Even though it seems like it might be very complicated at first, it's really pretty simple. Maybe I shouldn't say simple, but it's straightforward. So what is my upper bound then? It's going to be X bar observed 1000 plus, I need to compute a T number. I'll come back to that. S over root N, 3000 over root 31. And then for T alpha, so what do I have? I have a T index that I'm looking for that has an entire area alpha or an entire 5% in one tail. So this is a one tail alpha 5%. And my degrees of freedom, which T distribution am I working with here? My degrees of freedom is n minus 1, 31 minus 1, or 30. So I'm looking for the T index corresponding to a one tail area of 5% on the distribution, the T distribution with 30 degrees of freedom, 1.697. We notice that this is a smaller number than like the 2 to 3-ish that we got when we split 5% between two tails. Does that make sense? Well, sure, if I put more area in this right tail, that pushes this upper bound closer to the mean. That means we're fewer standard deviations or standard errors away from the mean. So this number should be like less than that 2.5 to 3 or so that we were finding before. And it is. It's down here at like 1.697. But it's not as small as Z would be with 5% area in one tail. It's not as small as 1.645. Remember that as a little side note, I said that as nu goes to infinity, as degrees of freedom go to infinity, t goes to z, we actually can find our z numbers off the t table. They give us this line at the very bottom of the t table where it just says degrees of freedom are large. Well, this is really the limit as degrees of freedom goes to infinity. And those numbers look very similar to these ones, right? A 95% confidence interval, which would be 5% combined area between two tails, 1.96 for the index. A 90% confidence level, which would be 5% area in one tail or 10% in two tails, 1.645, and 99%, which would be 1% area combined between two tails, or 0.5% area per tail. Well, this says 2.576 or 2.575, just a little bit of rounding difference there between the two tables. So we actually see that we can find z numbers pretty quickly using the t-table. So we don't even really need to refer to our z-table anymore for confidence intervals or hypothesis tests. At least not for this direction, if we're just looking up these critical numbers. Okay. But for our one-sided confidence interval, we just need to plug this into our calculator. So 1,000 plus 1.697 times 3,000 over, not times, over, square root of 31. I get all that in there, right? That looks good. And that is 1914 or so. So that's about 1,914 for upper bound. So this is our one-sided confidence interval. We are 95% certain that 1914 is above the true mean mu. We're 95% certain that an upper bound constructed in this manner will be greater than the true mean mu. Any questions on any of this? Okay, let's introduce the idea of confidence interval for variance and standard deviation. Let me again pause my screen share here for just a second while I bring up a different table. So now we're going to jump over to the chi-squared table, the other table that I had posted in chat and that's available on Blackboard. So let me get that brought up and ready to go. There we go. And this chi-squared table, this chi-squared distribution table is the one we'll be working with in this section, confidence interval for variance and standard deviation. So recall quickly that S squared is a good estimator of sigma squared, and for our purposes, we'll suppose that S is a good enough estimator of sigma that we'll treat it as a good estimator. We recall that, for instance, the random variable x bar minus mu over sigma over root n was approximately standard normal by the central limit theorem. So I had my random variable x bar related to my sample statistic, and I had my parameters mu and sigma. Those were the known quantities that I was interested in, maybe in the population. This was approximately standard normal. I have a similar relationship over here. It doesn't look the same. It's not the same mathematical structure, but it's a similar relationship in that it's some formula involving S squared, the estimator, or really here we're thinking of S squared being like the distribution of the variance of the sample variances. So this S squared is like a random variable, in the sense that if I took a sample, computed S squared for that sample, I'd get a number. And if I took another sample, another random sample from the population, computed S squared for that second random sample, I'd probably get a different number. So S squared is a random variable the same way that X bar is a random variable. So the sample statistic S squared, that random variable, when scaled by dividing by sigma squared, the population parameter, and then we have to multiply by n minus 1. When we do all of that, that gives us something that is approximately distributed according to this distribution. It's not a z distribution. It's not a normal distribution. It's not a t distribution. It's some other distribution. This is called the chi-squared distribution. The name of the distribution is chi-squared. So that symbol there, if you will, that set of pixels is the name of the distribution. It's the Greek letter chi. It's the Greek letter ch. Maybe more appropriately, something like key or something like that, but everybody calls it chi, so we'll call it chi. I wouldn't call it chai. If you call it chai, I don't think people would really know what you're talking about, but the chi-square distribution or chi-square distribution, something like that. So it's the Greek letter ch. Greek has some letters like theta, the th, that kind of represent what we represent with two separate letters. And the name of this distribution is the chi-squared distribution. So if I was to verbalize it, I would say chi-squared, or as a symbol, I would write it this way. But this is the Greek letter chi that looks a little bit like an X, although it has kind of like a curly bit. Like if this was the line, it's a lowercase letter and it's like little bottom tail goes below the line, like a P or a Q kind of, but you know, it won't be that careful with writing. Okay, so what is the chi-square distribution? Is it just kind of its own thing that's unlike any that we've seen before? Well, not really, actually. We can construct it using normal distributions. If I consider a normal distribution, a standard normal, if I take draws out of a standard normal distribution, I take one sample of a normal distribution, look at that number, and then I square that number. And I do that again and again. If I do that n times and add all of those numbers together, draw a standard normal, square it, draw another standard normal, square it, add all those together, do that for n of them. That's what a chi-squared is with, I think this is with n minus 1 degrees of freedom, if I remember right. Might be with n degrees of freedom. But that's what a chi-squared is. It's adding up normal distribution squared, standard normal squared. So what does it look like? Well, first off, it does not look like this. Well, because this has negative stuff, right? And if I square a bunch of stuff, it's non-negative. And then if I add it together, it stays non-negative. So it's not going to look, it's not going to have this bell curve shape to it. It's not going to be symmetric about 0. In fact, it starts at 0. It has nothing over here. It is only positive. The only way to get 0 exactly would be to get n standard normals, all of which are exactly 0. And of course, there's 0 chance of that happening. So it is, for all intents and purposes, always positive. Although it has a little bit of a feel of a bell shape. It does have this kind of this ramp up to a peak and then decline off. We see it goes out all the way to infinity, like the standard normal goes out to plus or minus infinity, but now we just flip everything over to the positive side because we're squaring everything. So it does go out to infinity. It has a hard stop at 0, cannot go negative. It is not symmetric. It is not symmetric about this peak. So we lose this crucial idea of symmetry of the distribution. And we have to take symmetry into account some other way here. But this is a chi-square distribution. This is what most of them look like. There are a couple of pathologic cases, like I think maybe 1 degree of freedom looks kind of wonky, but essentially all of them look this way. There are a differing number of standard normals that we can add up together, add their squares up. So we have different chi-square distributions. If n is larger, I get a distribution whose hump is further to the right and it's a little bit flatter. If n is larger still, its hump is even further to the right and it's a little bit flatter, although I probably should come back to 0 a little bit faster there. But this is what our chi-squares look like. And actually, it kind of, if you pick a pretty big n, it kind of looks a little bit like a normal distribution. And I think some people can, you can maybe get away with using some approximations in that vein, but we'll just use the chi-square distribution directly. So now we can ask, how do I construct a confidence interval for this? Well, I want to maintain this idea of symmetry. If I think of s squared as being a good estimator of sigma squared, I want to kind of take s squared observed as something like the middle of my interval and then kind of go out symmetrically on both sides. But the problem is going up or down a margin of error, just going up E and then down E to get my upper and lower bound, really relied on the symmetry of the distribution as well as the symmetry of being a good estimator. I don't have the symmetry of the distribution anymore. But I can impose a similar symmetry constraint, and that let's say that I'm dealing with a 95% confidence interval. I can make an upper bound and a lower bound with 95% in the middle. There's lots of ways I can do that, but to impose symmetry, I'll impose it such that the area in the two tails is the same. I lose the symmetry to be able to do just plus or minus a single number from, say, s squared observed, but I can certainly put 2.5% in this tail and 2.5% in this tail. These indices, these chi-squared indices, will be called chi-squared left and chi-squared right. So chi-squared left will have 2.5% area to the left. Chi-squared right will have 2.5% area to the right. Note that in the chi-square table, we have area to the right of the critical value. So chi-squared right has 2.5% area to the right, in this case, in a 95% confidence interval. And chi-squared left actually has, well, 2.5% area to the left means 97.5% area to the right. So I might be looking for chi-squared right down this 2.5% area to the right column, and for chi-squared left down this 97.5% area column. Okay, so we have this thing n-1 s squared over sigma squared that's distributed as a chi-square distribution. And we're kind of sticking that between chi-squared left and chi-squared right. That's our confidence interval here, this to that. We can invert everything. That switches the directions of the signs. We can multiply by n-1 s squared, and we get a confidence interval for sigma squared. That sigma squared is bounded below by n-1 s squared over chi-squared right, and bounded above by n-1 s squared over chi-squared left, again at the 95% level or whatever confidence level. These are, of course, not hard bounds. These are bounds for our confidence interval. Our degrees of freedom are still n-1. So just like with the t interval, degrees of freedom are still n-1. Remember, there are lots of these different chi-squared distribution. So which one are we on? That's going to correspond to one below our sample size. So that'll dictate the row that we're looking in. So if we had a sample of size 10, we'll be looking in the degrees of freedom 9 row, and then we might be looking to find 97.5% area to the right, or 2.700, and 2.5% area to the right, or maybe 19.023, for instance, for my chi-squared left and chi-squared right, respectively. And here's where we're cheating a little bit. If we want a confidence interval for sigma, the standard deviation, we'll just kind of square everything. This isn't, properly mathematically precise, but we're saying that, well, it's probably good enough for our purposes. Will probably be accurate enough most of the time that we're happy using this approximation. Okay, have two examples, and we certainly will not be able to get through even one of them, I think, in 3 minutes. So I think what I'll do is I'll post a supplemental video for just the last little bit of this confidence intervals for variance and standard deviation section. I think I'll post that on YouTube and on the playlist, and you can kind of watch that at your convenience, but we'll wrap this up in a supplement. And then when we come back, we will hit hypothesis test. So the last kind of major topic for the course that we'll jump into when we come back from the break. And yeah, so we have spring break next week. So enjoy the break. Like I said, I recommend not stepping fully away from the material for an entire week. Touch base with the material a couple of times, but otherwise enjoy your break. Let me stop the recording.